Hello and welcome again to my Physical Science online video lecture supplement series. In today's video, I wanted to look at a single relatively long example for the temperature and heat unit in our course. This is one of the longer examples that I do in this course, but therefore I decided we should have a separate video for it. Before looking at the example itself, I wanted to review a few of the important equations that get covered in this unit. Of course, in the textbook, these equations are usually published immediately above the exercises section of the text. I'm basically going to work an example that makes use of these two top equations. So there's two equations in this example. Therefore, it's one of the most difficult, or more difficult, I should say, examples that you do in physical science, because there are two equations rather than only one to deal with. So the example itself says, suppose you add some amount of heat to ice, 26 kilograms of ice, which is initially at 260 kelvins temperature. And the question is, what will the phase be of the ice? In other words, will it still be a solid ice? Will it have melted to form water, or will it have melted and then boiled and vaporized to form steam? So what will the final phase of this be, and what will be the temperature of the water or ice or steam after it has absorbed all of this energy? And as always, we're assuming that all of this energy is really going to heating the ice or melting it or vaporizing it. All right, so let's go ahead and write down our first equation, which says that the amount of heat added should be equal to the mass of the thing being heated times the specific heat times the change in temperature. And bear in mind that if we get over 13 kelvins worth of temperature change, we will have reached the melting point of ice. So the initial temperature was 260.0 Kelvin, and at a final temperature of 273 Kelvin, it melts. So we get a phase change. So how much energy is it going to take to reach that phase change, in other words? So we can write that 13 kelvins worth, or let's solve it for how much heat you need to get a 13 Kelvin temperature change. The heat should be equal to 26.0 kilograms times the specific heat of the ice. And so we should probably look up what the specific heat of ice is. That's basically listed here in this table. Since we're working in joules, we want this column, so it's 2100 joules per Kelvin degree C. And of course, 1 degree C change is equal to 1 Kelvin change, so this is also 21 joules per kilogram Kelvin. And our change of temperature of 13 Kelvin would bring us to this melting point. So let's see how much heat this takes just to get to the melting point of the ice. So 26 times 2100 times 13 gives us 709,800 joules. So we'll call this sort of the heat used up in phase 1. And that was 709,800 joules. So how much heat do we have left over at this point? Well, we have taken this much heat out of our initial, the amount input, recall, was 1.0400 times 10 to the 7 joules. So if we want to figure out how much heat we have left, we use heat left over is whatever the heat input in minus the heat for this phase 1. So the heat in this phase 1 we could write, for example, as 7.098 times 10 to the 5th joules. And so if we wanted to convert this thing into a times 10 to the 5th, it would look like 104.00 times 10 to the 5th joule. So that means that the difference, what's left over, is the difference between these two numbers. So after basically melting the ice, after getting the ice to melting temperature, we're left with 9.693 roughly times 10 to the 6 joules. So basically we're just subtracting this number from this number and then rounding as appropriate. This thing right here should be a 2, not a 3. So then from there, we now need to melt the ice. So melt the ice. And to do that, we use that second equation. The heat to make a phase change is equal to the mass times the latent heat. In this case, it's latent heat of fusion. So we need to look up the latent heat of fusion for going from ice to water. So we can get that from table 5.2 from the Shipman, Wilson, Higgins, and Torres Introduction to Physical Science text. So the latent heat of fusion, this is given in kilocalories per kilogram. And for water, it's 80. So what we have here then is 26.0 kilograms times 80 kilocalories per kilogram, which we should probably convert over to joules per kilogram. So we use 4,180 joules per kilocalorie. So this tells us in joules how much our melting the ice is going to take heat-wise. So now we go ahead and pull out the calculator again. So we have 26 times 80 times 4,180. That's 869,000. That's 8,694,400. So let's write that in scientific notation down here. This was the phase 2 heat, or the stage 2 heat, and we can put 8.6944 times 10 to the 6 joules. And again, we could round that at the end. We're going to be subtracting that from the amount of heat that we had left over from the previous stage. So at this point, we have heat left from stage 2 is heat left from stage 1 which is this guy here, minus the heat used in stage 2. That's the same as the heat in minus stage 1 minus stage 2. So when we do that, we end up getting that we should have about 9.87 times 10 to the 5th joules left for heating water. Okay, so to heat the water, we go on to stage 3. And in stage 3, we're going to just heat the water. So what we're going to need to do for that is use the equation that heat is equal to mass of water times specific heat capacity for water times change in temperature for water. So strictly speaking, we could check to see how much heat it's going to take to get up to the boiling point. And to do that, we basically need to know what this specific heat capacity is for water. So we need to go look that one up. We get that specific heat capacity of water from table 5.1 in the Shipman et al. Introduction to Physical Science text. That's the same place that we got the specific heat capacity for ice. For water, of course, it's 1.00 kilocalorie per kilogram degree Celsius, or 4,186 joules per kilogram degree Celsius. This also, by the way, is where you get the conversion factor that I was using from kilocalories to joules. Since these units are the same, then the conversion from this unit of kilocalories to this unit of joules must be from 1 to 4,186. I kind of truncated it to 4,180, so in case you're wondering where that one came from. Alright, so the heat needed to get to boiling would be 26 kilograms of water times 4,186 joules per kilogram Kelvin times 100 Kelvin. I think what we're going to find here is that that exceeds this amount of heat that we have left, so we can recalculate and just figure out what the delta T is. But let's go ahead and plug these numbers in to make sure that that's true. So 26 times 4,186 times 100. And sure enough, this number exceeds this number. This is well over that 9.87 times 10 to the 5th. So what we need to do is figure out what temperature change we have in this water. So we're going to rearrange this equation. So this is greater than 9.87 times 10 to the 5th joules. So we rearrange the equation to say that we're going to solve for delta T. So delta T is equal to H left from stage 2 divided by the mass times the specific heat capacity. Alright, so that means that we have 9.87 or 987,000 joules, and we're dividing that by the mass, 26 kilograms, times that specific heat capacity, 4,186 joules per kilogram Kelvin. And of course what we're going to find here is a change in temperature in Kelvin, which is also equal to the change in temperature for degrees C. So we need to put all these guys into our calculator to get an answer. So let's start off with 987,000 joules. We're dividing by 26 kilograms, and we're going to divide that by 4,186 joules per kilogram Kelvin. What we get is 9.06869 blah blah blah. Really, we should be putting out about 3 significant figures here. So we can say 9.07 Kelvin. Okay, so that means that the final temperature is 273 Kelvin plus 9.07 Kelvin. So the final temperature is going to be that plus 273 gives us 282.1. So we can write this as 282.07 Kelvin, and since that 273 is a rough approximation, we can just round it to that the final temperature is 282 Kelvin, or if you will, 9 degrees centigrade. So that means that the final state of the ice after adding this heat, this 1.04 times 10 to the 7 joules of heat, is going to be liquid water. So this will be liquid water at 9 degrees Celsius, or if you want, at 282 Kelvin. So that's it for this example, and thanks for watching. I hope you found this video helpful.